When we were discussing propositional logic, we saw that we could write statements like this. A was equal to 5 is greater than 10, or we could have B is equal to 73 is greater than 10. And each of these had a truth value, right? 5 greater than 10 is false. 73 greater than 10 is true. And we also could do things with truth tables, so we could have more complex expressions and determine the truthfulness, that is, whether or not the whole expression was true or false, by using our truth tables. And eventually we learned to work through logical statements by reasoning through it and determining the truthfulness of it without having to build a truth table. The problem, though, is that propositional logic is not set up to represent statements like this. All integers are greater than 10. We know this is a false statement. It's not true that all integers are greater than 10, but I don't have a way to represent that really with propositional logic. So now we're introduced what's called predicate logic. And in predicate logic, we're going to have a domain, and some people say this domain of interpretation. We would have quantifiers, and we also have predicates. So what are each of these? The domain would be what we're applying things to. So the domain could be something like all objects in the world, all animals, the set of integers, and so on. Quantifiers are things that will let us represent things like all, or there exists. So we have the universal quantifier, universal. It's written as an inverted A, okay, and is typically used with implication. And then we have the existential quantifier, which looks like a reverse capital E, and it's typically used with logical and. Okay? So what do each of these mean? Well, let's write this down. So for the universal quantifier, in English, we'd have things like this. For all, for every, for any, for each, and probably some others. And then for the existential quantifier, in English, this would be written as things like there exists one, for some, for at least one, and so forth. Okay? So these are quantifiers. Now finally, for predicates, these are the way that we represent properties. So we might write this something like P of x, and x here is a dummy variable. P of x might represent x is blue. Or we might have, capital E of x represents x is an even number. And once again, this would be applied to a particular domain that x is drawn from. Okay? So let's look at a couple of examples. So let's start with our domain. This would be a set of positive integers. And so let's write existential quantifier x inside parentheses, and then P of x, and what P of x means is P of x is prime, right? And so this statement right here in English says that there exists an x such that x is prime. Since our domain here's a set of positive integers, is that true or false? Well, certainly it's true, because all the primes come from positive integers. So there's at least one there that's a positive integer. So this would be true. If on the other hand I wrote this, which translates into for all x is prime, this is false. Because if x is a set of positive integers, this is claiming every single positive integer is a prime number, which is clearly not true. Okay? Now we also can create more complex expressions by combining, additional predicates and additional quantifiers. So let's say we have something like this. So our domain again will be set of all integers. We'll say that P of x, y, right? Because now we have multiple things that have properties, is x squared is equal to y. And what if I wrote this? What we're demonstrating here is that order of these quantifiers matter. So this translates into, for all x, there exists a y such that x squared is equal to y. Is that true or false? Well, this is saying, for all x comes from a set of integers, as does y. They're from the same domain here. For each x, if we were to square it, do we get another integer? Well, yes, certainly. 2 squared is 4, 10 squared is 100, and so forth. I'm always going to get an integer when I square an integer, right? If on the other hand I wrote this, if I just swap the two here, now this says there is a y such that it is the square of all integers. Well, that's a different thing, and it's also false, so this was true. This is false. It's claiming that there's some integer that you can pick, and it will end up being the square of every other integer. Well, that clearly can't be true. Okay? So I've taken the same things I had in both places, but just swapped the order of the quantifiers here, and it totally changed the meaning. So you have to be careful about how you're using these. But here in the upcoming video, we'll start seeing how to do additional things with the quantifiers.